So welcome back. In the final lectures, we're going to take a tour of some results in the theory of symplectic manifolds and Hamiltonian G-spaces. I'm going to quote to you some theorems and also illustrate these theorems with some rather interesting examples. The theorems themselves are very intricate. Their proofs are difficult and often span several pages. So we won't be covering the proofs of several of the results I'll mention. But at this stage, you actually have enough background material that you could probably follow along the proofs in either in the original papers now or indeed several books. And we've been thinking about Hamiltonian G-spaces in these past couple of lectures, and that is, these are associated to symplectic actions of some group on a symplectic manifold, and we have this thing called the moment map, which is like the all-purpose Hamiltonian generating the vector fields coming from these actions. Now, in today's lecture, we're going to look at some properties of this moment map, some rather striking structural properties that the moment map has. And in particular, we'll look at also some examples. And the first such result that we're going to look at today is the image of the moment map. What kind of structure does it have? What does it look like, the image of the moment map? It turns out that under some conditions, the image of the moment map is a convex set, which is sort of rather striking. If you think of a symplectic manifold as being some rather curved, nonlinear looking thing, then the moment map's image being a convex set in the dual of Lie algebra already seems rather striking. I mean, it's not always true. There's a couple of adjectives we have to add before this result will become true, but they are arguably reasonable on a physical level. All right, so let's start with just a compact connected symplectic manifold. We'll probably drop the connectedness fairly easily. Compactness you can't drop so easily. And suppose we have a group acting on this manifold via symplectomorphisms. So our group is going to be the n-fold torus. An M torus, sorry. We have our manifold, which is some curvy surface maybe, and we have a group acting on this manifold, pushing all the points around, acting by symplectomorphisms. And that group is not just any group, we're going to take it to be this torus group here. Acts on the manifold, you give it an element of the M torus and it'll push around the points of the manifold in a smooth way such that the symplectic form is preserved. we see what happens. So to every one parameter subgroup of the torus, there's a circle action now on the manifold. We can associate with that action a vector field, and then the moment map is the object which gives us that vector, is the Hamiltonian for that vector field. Has a moment map, which is a map from the manifold to the dual of the Lie algebra. It's just here denoted T star, and T star is equivalent to Rm in this case. And there's three things that we can observe about this moment map, the image of this moment map. So if you take mu acted on all of M, then it's going to give you a whole bunch of points inside of Rm. And this image, the image of M under mu, that's the interesting, the object of interest here. Okay, the first observation is that the levels of mu are connected. It's not entirely self-evident. The second observation we make is very striking. Namely, that the image of this manifold M, no matter how crazy that manifold is, the image under mu is convex. And furthermore, even more striking than that, is that this is not just any convex set, but it's the convex whole of a bunch of fixed points of the action. So you find the fixed points of the symplectic action here, and then you find the image, and then you take the convex hull, and that is the image of mu. So who ordered that, right? That's a very strange property that's true about these moment maps. Very powerful property indeed. Certainly won't prove it. You prove it by, one way is to prove it by induction on M. But it relies a little bit on advanced methods that we haven't discussed in enough depth. So instead of proving it, what I'm going to do is give you two examples of this theorem. And I think you'll quickly get a sense of why these statements should be true. In fact, these examples are going to recur throughout this lecture. So the first example is not an example. So this is a this is always somehow strange exceptional case, and that's the harmonic oscillator. So the harmonic oscillator is a kind of a non-example. But the harmonic oscillator is so has so many nice properties, it ends up sort of illustrating these results in a very convenient way. So this is the non-example. So the Hamiltonian is a half x squared plus y squared. And m, so the Hamiltonian is the moment map in this case, right? M is just R2, and omega is just dx wedge dy. Okay, this is our go-to example for illustrating things in symplectic geometry. And we're going to look at the image of mu. So mu is just a map from R2 to R plus, which is a subset of R. And it's a non-example here in particular because, well, we'll see. Right. So you have phase space here. This is the harmonic oscillator's level sets. Okay, let's check the property of these levels. Are these levels connected? Yeah, they look pretty connected, don't they? Is the image of mu convex? Well, let's find out what the image of mu is. What's the image of mu under this? Well, if you take the real line, it's all points to the right of 0 and including 0. So an interval, even an infinite interval, is convex, so yes, that property is true. And the third one is sort of where this exhibits itself as a non-example. The image of mu is the convex hull of the fixed points of the action psi. Okay, so if we look at psi here, psi is the action, the dynamics of the harmonic oscillator. Well, indeed, one of this set here is a convex hull, and indeed one of the fixed points of psi is an exterior point of this convex set here. But like this convex set here is the convex hull of 2 points, namely the one at infinity. So this sort of doesn't quite work as an example. We could compactify R2, like add in infinity. And then if you take R2, compactify it with 1 point, not with 2 or 4 or whatever, but with 1 point, then that point at infinity would also be a fixed point under these dynamics, and then this theorem would become true. We're going to do that actually basically in the next example. If you compactify the plane, you get the sphere if you take a 1-point compactification. So the plane has got many, many remarkable, exceptional properties, right? You can think of it as the complex numbers. You can compactify it with 1 point to get the sphere. The sphere is a complex manifold. Lots of good stuff. The sphere is also symplectic. It's certainly enjoyable to think about what would happen if you had a torus action on a 4-dimensional plane. So you replace R2 now with R4, and you have a torus acting on that space. It's interesting to think about the level sets there. Anyway, let's go to our proper example now, which is motivated by this non-example, namely we just compactify the plane. And then we choose some friendly symplectic form that we like. So we're going to take S1 to act on the surface of the sphere, and we're going to use coordinates, angle and height coordinates. Here's the sphere, and the action of the circle on the sphere is to just rotate the sphere. So the group acts by rotating the sphere in this direction. We have some coordinates here, -1 to 1. This is height. The y-axis is the height coordinates, and you've got angle coordinates here, which we'll measure from this picture's a bit awkward to draw the angle coordinates on. Angle coordinates there around this height axis. And the moment map is just the height. So let's check. Are the levels of mu connected? Well, again, they're circles, right? So yes, they're connected. Is the image convex? Well, the image is easy to work out. It's just the interval -1 to 1. Certainly a convex set. And is this convex set the convex hull of the fixed points of the action? Absolutely, right? So there's two fixed points of this group action, the north pole and the south pole. And the images of those 2 points are -1 and 1, and they are indeed the extreme points of that convex set. So that's another example of this theorem in action. The intuition you should carry with you is that mu is really the energy. So the energy of any dynamical system, you can, as long as it's sort of bounded from below, you can make it a positive function. And this theorem says that the image, there is an inverse image for all energies between 0 after rescaling and some upper bound. That's the first of the several remarkable properties that I want to mention. The next one concerns the Liouville measure. Let's prove a very powerful theorem in less than a line. As I write it, you'll see the proof. So the Liouville measure, that's something that should be familiar from your studies in classical mechanics, is a way of measuring area in phase space. Area is proportional to action, right? Now, the natural generalization of the Liouville measure from the classical dynamical setting to a general symplectic manifold is just to realize that the symplectic form itself gives you this notion of area. Remember, the way I introduced this all the way at the beginning of this course is that symplectic geometry is the theory of oriented areas. So let's just write down the area implied by a symplectic form, and it's just this guy here. You wedge up omega with itself n times. And that's guaranteed to be non-zero because omega is non-singular by the very definition of symplectic manifold. So we have this canonical volume form on any symplectic manifold with which we can measure area or volume, more correctly, volume. And this definition here already tells us, I mean, as I erase the board, you'll be able to prove this in your mind, that if you have a flow generated by a symplectic vector field, this volume form is left invariant. The statement of this result, Liouville's theorem, takes longer than the proof. Very beautiful. When you get the right generalization, this good results come easily. This is no exception. What happens as a vector field operates on a manifold? Well, you know, moves things around. So let X be a symplectic vector field. This vector field generates a symplectic flow on the manifold. Then, well, what's the definition of symplectic? Well, it's that the Lie derivative of the 2 form is 0. Right? That's what it means, symplectic. Then what that tells us is we learn that the volume form is left invariant by a symplectic flow. Just use the Leibniz property here, and you're done. It's fantastic. So that shows us that symplectic flows leave this notion of volume invariant. And this is called Liouville's theorem. Right? So this is, if you think of symplectic flows like dynamics, this tells us that the Liouville measure is the correct invariant measure. With which to assess volume in phase space. Really is a very remarkable result. You could choose some incredibly complicated Hamiltonian dynamics or symplectic flow on a manifold. The picture you're probably familiar with, you have some symplectic manifold, and then you look at some initial piece of the symplectic manifold, and then you let dynamics run for a long time, so you let psi be some symplectomorphism, very, very complicated, possibly symplectomorphism, and this distorts this little square all around the manifold. So this might get, squished and stirred and mixed up. And no matter how complicated this map, the volume of the image, which here looks enormous because of my bad drawing, is exactly the same as the volume of this initial square here. This is meant to be very thin. You get the idea. This is an interesting measure. We should look at this measure a bit more, right? It's got some nice properties. All right, to get further on this game, we're going to have to, again, assume that our manifold is compact. We compactify it in a symplectic way, if it's not. This has some very important consequences. One of them is that the Liouville measure becomes finite. This will help us tremendously, although everything ends up being generalizable to non-compact case, but let's just make our lives a little bit easier. So you can integrate the Liouville measure over the whole manifold, and you still get you just get a number, and it's not infinity. Now, if that's all we had, then that's all we'd do, right? But we have more. Let's suppose we have now a G-space, Hamiltonian G-space. Well, let's just start with Hamiltonians. Let's suppose we have a Hamiltonian now on our manifold. Remember, a Hamiltonian is nothing other than a real-valued smooth function on your symplectic manifold. Now we've got two spaces. We have our original symplectic manifold, and we have the image of the energy function, which we know to be convex, and the convex hull of the fixed points of the energy. Let's use this map to induce a measure on the space R. So if you have a measure, some way of measuring volume, on a space, and you have a map to another space, then you can get another measure on the target space called the push-forward measure. Okay, I've just realized they've used the same symbol for the push-forward measure as the moment map. Let's call it little m then. So the little m is the push-forward of the Liouville measure onto the target space. Now, I knew this was going to confuse everyone. It's not. Why not capital omega? As, I don't know. Why not? I don't know. I like little m. Little m stands for measure. M. So we can induce a push-forward measure on R. And the way it works is you let, if you You can sort of work it out, right, from what it has to be. So let A be some measurable set. We'll just take our favorite measure space on R, the Borel measure space. So let A be a measurable set in R. Then this push forward measure, what is it? Well, you've got to work out what's a canonical way to measure the area of A in R using the data we have at hand. And the data we have at hand is H, which is a map from M to R, the set A, and a measure on M, big M. So what we can do is we can take A and find its pre-image under the Hamiltonian, some subset of phase space, and then measure the value area of that. And that will indeed be our measure. So we're like saying this measure here, little m, is telling us what's the area of all the states in phase space whose energy lies in some band. That's the physics behind this measure. What proportion of phase space has energy inside this band A, if indeed A is an interval? So let's define now this measure. Little m of A is defined to be the integral over the pre-image of A, so the set of states with energy in A. And how do we measure area? Well, with a Liouville measure like that. The proportion of phase space whose energy lies in A. So a pretty physical question to ask. This measure's got a name. It's called the Duistermaat-Heckman measure. Now the Fourier transform of the Duistermaat-Heckman measure is a very interesting object indeed. It's got to do with path integrals.
One question.
Yeah.
We said that A, I think it's behind this spot, A is measurable.
Mm-hmm.
How much of an effect does it have, what we understand of measurable there?
So you're basically asking what's the measurable space and does it depend on the measurable space? So just take your favorite, the canonical one on R, okay. So the Borel measure space on R. Yeah, it certainly does depend on what measure space you take here. If you take some absolutely bananas measure space, then what I'm going to say will certainly not depend. Will certainly depend on that.
Okay, but if we could choose any measure space,
I mean, so far this equation makes sense for any, as long as H is a measurable map, as long as we have a measure space over here, and as long as the I mean, for H to be a measurable set, it needs to be that the these sets H minus 1 of A are also measurable according to this measure here. And this one here is really Lebesgue, right? On not quite Lebesgue, we're on a manifold, but the equivalent Borel measure space there. So there's the definition of measurable function already puts some constraints on what kind of measurable spaces you can have here. But for this, just take it now to be the standard Borel measure space on R. Okay. And we can postpone that interesting academic discussion to a research paper. Right, so we got this, we can induce a measure on R, the space of possible energies that our states can have. Now, H can be anything, right? H is seriously just any measurable function here. So we don't really think, a priori, there's no reason to think that this induced measure here has any nice structure. So I want to emphasize that M looks pretty arbitrary. And indeed, for the non-compact case, it is pretty arbitrary. But let's make things slightly less arbitrary and focus on the circle case. So often Hamiltonian actions are circle actions. Like, after some time, the trajectories close into circles. This is not an unreasonable assumption. It's reasonably physical. So that means that the flow generated by the vector field X, which is the vector field coming from H, is periodic. I think I used L here, yep. There you go, after some L it repeats. I mean, you can do very, very crazy things. Just as long as after some unit of time L, the flow returns to itself. In this particular case, we can say a lot more. Okay, here's the result. Quite an astonishing result. Suppose we have some symplectic manifold, an even dimensional compact symplectic manifold, and you let H be any old Hamiltonian as long as it's an S1 action on that symplectic manifold. Then this measure here, this induced measure, isn't just any old measure. It's a polynomial multiple of the Lebesgue measure on R. There is some conditions, of course. This statement isn't true everywhere, but you've got to be near a regular value of H, so the derivatives are defined. And further, this polynomial has degree less than or equal to n minus 1. It's not even a completely crazy polynomial. This degree is induced by the dimension of this manifold M here. And let's just make a really simple observation. The only place where H is irregular is on its critical points, and it's not unreasonable to assume that H has only a finite number of critical points. Then this tells us that the induced measure on R is a piecewise polynomial pretty amazing. Proof's a couple of pages long, but the elements of the proof are to look at the pre-image of a regular point inside M, and then look at a kind of little neighborhood around that and regard that as a circle bundle. And then you look at the measure of the circle bundle and you relate it to a connection on the circle bundle, and then you see that the area has to be is only classified up to a cohomology, and then you can more or less drag the result out from that. So it's a very, very rough sketch of how the proof goes. I won't prove it. So we'll just look at examples, see how it works in practice. That's where the beauty of this result comes anyway. So I've seen the Duistermaat-Heckman theorem or proposition here exploited to variously evaluate path integrals exactly. So we won't do that in this course, but by taking the Fourier transform of this measure here, then you get an integral which looks like a path integral, and this result tells us that integral, if you evaluate it with stationary phase, you get the exact answer. So that's one place where you can use Duistermaat-Heckman. You can use it to evaluate path integrals also in quantum field theory. So this is finite dimensional, but there's an infinite dimensional version at your disposal. Bunch of other places like that. You can use it to evaluate random matrices and generating functions for random matrices. So it's, as long as you have a symplectic action and you have something that you want to measure the area of, then the Duistermaat-Heckman theorem may very well be the most useful tool for you. fantastic result. We're going to begin, just as before, with a non-example, because it's just most cleanly illustrates everything, even though it's not quite fulfilling the requirements of the result. So again, we let m be R2 and omega be dx dy, and we look at the harmonic oscillator. So the Liouville measure is just dx dy over 2 factorial, oh no, 1 factorial. And then we let H be our harmonic oscillator Hamiltonian. And then let's look at the level sets and look at the area of the pre-image of some range of energies. So we know that the vector field generated by this Hamiltonian, we've done this in examples and exercises, it's this guy here, y d dx minus x d dy. And we know the Hamiltonian action is periodic. Now, I'm not going to explicitly compute the push-forward measure. I'm just going to argue how the push-forward measure looks just by looking at some examples. It's basically a proof, but one or two steps are missing. So let's look at the image of the Hamiltonian. That's this half space here. And let's look at the pre-image. So if we take 2 points here, A alpha, let's say, and beta here, I'm going to look at the set A alpha comma beta. Let's look at that set. And I guess let's look at the half open set, just to make the connection with measurable sets a bit clearer. So this is some subset of R, which is R plus, which is a subset of R, right? So let's ask what proportion of phase space has energy lying in this band alpha to beta. So you have to undo this map H here. So H is this map a half x squared plus y squared. So we're really looking at an annulus in phase space. So that's the pre-image. That's H minus 1 of A. It's an annulus. And the two internal radii, the internal radii, sorry, is root 2 alpha and root 2 beta. That's the two radii, the internal and the external radii of this annulus. So let's work out the area of this pre-image. Well, you work out the area of the outside circle and you subtract from it the area of the inside circle, and you come up with the number 2 pi times beta minus alpha. You already see this theorem in action. If you look at beta minus alpha and you ask, how does that relate to Lebesgue measure on the real line? Well, the answer is, it is Lebesgue measure on the real line. And there's a factor of 2 pi, overall factor of 2 pi, but that's common to both spaces, so we'll drop that. So, it's true for the harmonic oscillator. So, the Duistermaat-Heckman measure is a polynomial multiple of Lebesgue measure. And it's worth commenting that this measure here is the push forward onto R plus of the map T goes to 1 over 2 pi T. Seems trivial observation, but we'll see that that has manifests itself again and again in the examples. So it's true for the harmonic oscillator, but then everything's true for the harmonic oscillator. There's nothing to learn here. Just about any conjecture you make will be true for the harmonic oscillator and false for everything else. So we have to look at some more serious examples before we can start to become convinced that things are true in general. So we'll do something that's not quite much more difficult. We'll look at r to the 2n instead of r to the 2. And we'll take our Liouville measure on this space. And we'll let the Hamiltonian be not quite the harmonic oscillator now, but like a sum of independent harmonic oscillators. So already you see here some slight surprises. So a Hamiltonian function is that of n independent harmonic oscillators. Then the vector field generating this flow is just the sum of the vector independent sum of all these vector fields that generate the individual harmonic oscillator flows. That. And the flow is indeed periodic with period 2 pi. So H is a map from R to N to R, and now we want to look at what's the push forward measure now under this function. Well, I'll do the same kind of argument as before. We'll look at the preimage of a point and then work out the volume of an interval. So what's the preimage of a point under this map? Well, it's just a set of all tuples with energy equal to R. Okay, so that's the surface of a sphere in 2n dimensions. a bit odd, right? You think of it as like maybe like a torus, but actually it's the surface of a sphere. So the preimage of a point is the surface of a sphere in this symplectic manifold, and the preimage of an interval then is the volume between two spheres. And that's where we'll work out what the Lebesgue measure is. What the Duistermaat-Heckman measure is. So, the volume of phase space with energies lying between alpha and beta is the volume of the sphere with radius root beta minus the volume of the sphere with radius root alpha.
Not root 2 alpha?
Oh, yeah. I think you might be right. There is indeed a 2, isn't there? 2. I had that in the previous example as well, yeah. 2 beta and 2 alpha, yeah. And you can do a little bit of integration on spheres to work out that that's equal to beta to the n minus alpha to the n. That's a little exercise in working out the volumes of spheres. And that is equivalent to this integral here. So look at that, that's a polynomial, multiple of Lebesgue measure, and the degree is n minus 1. So it's like the extremal case. Okay, you still might be skeptical that this is just the miracles of harmonic oscillators. Let's do a final example. It's a little bit more intricate. Look at our favorite example of the sphere, S1 acting on the sphere. So we're going to argue that the Duistermaat-Heckman theorem is a generalization of a theorem of Archimedes.
Sorry, maybe I'm wrong. Don't you miss the prefactor in the integrate? If I integrate
over n. Oh, so the question is, don't I miss a prefactor here from the integration? Yeah, that's a good point. So the factor should be n, right? Yeah.
Not there.
It cancels out.
No, there it's not, right? Yeah, of course. Yeah. Okay. Okay, I may have made an error there. So it's an exercise to check it, but the core result will be still that it's a polynomial multiple. The constant of proportionality I may have gotten wrong there. No, it looks right now. Well. All right, we're going to take the sphere. It's the same as our previous example with a slightly different coordinate system. So Liouville measure is just sine phi d theta d phi. And we're going to let our Hamiltonian act on this symplectic manifold, the sphere. Choose a particular Hamiltonian. We'll choose one that's not a polynomial. H is no longer a polynomial function of the coordinates. Where here is previous examples, it was a polynomial function of the coordinates, so maybe the polynomial factor over here had something to do with that rather than, say, the Duistermaat-Heckman theorem. But now we're going to choose something that's legitimately not a polynomial. So we're going to look now at the pre-image of H of some interval. So we have to integrate between alpha and beta, but remember we're taking now the pre-image of this interval on the sphere. So this interval, the pre-image on the sphere, is a band around the sphere like so. So we're looking at the volume of a little band around a sphere. Under this measure sine phi d theta d phi. And, well, it's perfectly set up to do a substitution, this integral here, and we end up with the result Did I actually do this? Yes. Substitute W equals cos phi. See, the coses here more or less tell you the substitution to make. But that's just a polynomial multiple, once more, of the Begg measure. Not even a polynomial, right? A linear function. And this is also recognizable as a theorem of Archimedes. That the volume of a band in an inscribing cylinder is the same as the volume of a band in a circle. So if you like, Duistermaat-Heckman includes that as a kind of corollary. Okay, and to end today, I'll just write out the full result. This was the general case. That was a special case of Duistermaat-Heckman. Now we'll write out the general case. The general case of the Duistermaat-Heckman result concerns now a torus action, so not just a standard Hamiltonian action by one vector field, but really, if you like, n independent vector fields. So you'd have a symplectic manifold, it has a torus action, and the torus is a d-dimensional torus. And it's a Hamiltonian G-space, meaning there's a moment map, which satisfies all the requirements of a moment map. T star here is proportional to Rd, because the Lie algebra of the d-dimensional torus is just R to the power d. Then, in a sufficiently small neighborhood of a regular point of mu, this Duistermaat-Heckman measure is a polynomial multiple of the standard Lebesgue measure on T star with a degree n minus d. So the bigger d, the lower the degree. Also a striking consequence here. Now, of course, it's easier to think up pathological examples here which can violate this. So mu might have like a line of critical points, and mu can be complicated. But as long as you're away from critical points, everything is polynomial measures, polynomial multiples of the Lebesgue measure. So that's the theorem. As I said, it finds applications in a variety of places. And certainly by far the most interesting advanced topic is evaluating oscillatory integrals with stationary phase. So if you have an oscillatory integral and you can somehow realize it as the Fourier transform of one of these measures, then you can evaluate that oscillatory integral using stationary phase, and this theorem tells you that the result is exact. So it's very rare that stationary phase gives you the exact answer, but whenever you can write your oscillatory integral as a Fourier transform of a measure like this, then you're good to go. That's probably the most sophisticated advanced example I know. It also has multiple generalizations as to supersymmetric manifolds, all kinds of stuff. It's really one of the core tools that we have in evaluating path integrals for integrable systems in field theory, and infinite dimensional generalizations as well. Okay, but I'll stop here today with this theorem. In the coming lectures, we're going to look at our final topic, which will be complex manifolds. So complex manifolds are a nice place to look for symplectic manifolds. They play very nicely together. And we will also look at quantum mechanics as itself as regarded as a dynamical system or a Hamiltonian G-space. But for now, thank you very much.